Welcome to part 3 of this series about integers in GDScript 2. Part 1 covered the what and why of integers. Part 2 covered integer arithmetic, overflow behaviour in arithmetic, and maths with other data types. This part is about bitwise operations on integers, and, as promised, I will explain how negative integer values work at the end of this episode. So, what are bitwise operations? Well, the clue is in the term itself. Instead of operating on the value of the integer as a total number, bitwise operations work directly with the bits in the integer. This is where knowing how an integer is stored as bits is particularly useful. The 64th bit is still the one that indicates positive or negative values. This does not change just because we're doing bitwise operations. There are two types of bitwise operations, Boolean operations and shift operations. If you know what you're doing, bitwise operations can actually be combined to produce arithmetic operations, because that is exactly what a CPU does. Let's look at Boolean bitwise operations first. We have AND, OR, NOT and XOR. As you can see, the operator characters are the ampersand, pipe, tilde and caret characters respectively. These operators only work with integer literals and variables. Attempting to use them with other data types will cause an error. If necessary, you can use casting to force a variable or expression to return an integer so that it works with one of these operators. The previous part of this series, part 2, has information about casting if you're not familiar with that concept. Although they are conceptually related, these operations should not be confused with the basic Boolean data type and Boolean comparisons, which will be covered in another tutorial. Bitwise Boolean operations on integers work by comparing the set and unset bits in the value and doing something based on each bit position. When we say set, we mean that a bit is set to a value of 1. On the other hand, an unset bit has the value of 0. This also corresponds to true or false when using bool variables. The easiest thing to do is show a bitwise operation graphically so it makes sense. Let's start with the AND operator, which uses the ampersand character. Here are the bits for decimal value of 147 as a 64-bit integer. Here are the bits for the decimal value of 85 as a 64-bit integer. As an aside, remember that the first bit is the least significant bit. As with a lot of things in computing, we count bits from 0, not 1. So the first bit is bit 0. Conversely, the most significant bit is the 64th bit, which is bit 63. Anyway, in our AND operation, what we're asking is if each bit in the first number is set and each corresponding bit in the second number is set. As we can see, bit 0 is 1 in both cases, so the output from the AND operation for that bit is a set bit, and so on until we get to our AND result of 17. You may be wondering why this is useful. Well, imagine that instead of just a number, you are using an integer variable as a sequence of on-off flags for something. This is not unusual in programming and is a very good way to reduce storage requirements for very large data sets. Let's say you use bit 12, corresponding to decimal value 16,384 if it is set, to indicate some condition. To see if bit 12 is set, you just need to use AND to compare your integer to the value 16,384. If you get a value of 16,384, you know that the bit 12 flag is set. If you get a value of 0, you know that the flag is unset. In addition to AND, you can also use OR, NOT and XOR. In particular, where AND is useful for reading a bit, OR is useful for setting a bit. NOT takes a single operand and flips all the bits. In terms of numeric value, it is equivalent to adding 1 to the integer and then taking the negative value. Again, this goes how to negative numbers are stored, which I'll come back to in the last segment of this episode. But in general, if we are just using an integer for bitwise operations, the numeric value doesn't really matter. All that matters is which bits are set or unset. However, being aware of how the numeric values are affected by bitwise operations may be helpful when you're troubleshooting. XOR, or exclusive OR, is the opposite of OR. For each bit, it gives an unset bit if they are both the same, and a set bit if only one of them is set. We have already seen how AND works, but let's jump into Godot to see how the other operations work for real in GDScript. Note that Godot does not have a built-in way to show all of the bits in an integer in binary format, so this project has a helper function to do that for us. This will make it easier to see what is going on in each operation. I already have a bunch of examples set up, so let's just run the project and see what we get. So click run. As you can see, the output just goes to the output window, so we don't need this. We scroll back up. So we've got a few examples of using OR here. In this case, we're comparing the bits in the values 10 and 5, and as noted previously, you'll get a set bit if one of the bits is 1 or the other bit is 1 or both of them are 1. So as you can see, the bits alternate between 1s and 0s here, so we end up with 4 1s, which is equivalent to 15 in decimal. In our next example, we're comparing 10 with -5. And we get -5 because the only bit that isn't set in both numbers is bit 2, the third bit. Carry on. If they're both negative, because all the bits above these 4 bits are set to 1, so we get all 1s. And in fact, all of the bits end up set as 1, which is equivalent to -1. And this is why it's best to ignore the actual numerical values of integers when you're using these Boolean operations, because, as I said before, what matters is the value of each bit, not the overall value of the number. Just for completeness, we've got a few comparisons of 0s and 1s here, as in the value 0 and the value 1. So we've got 0 and 1, 0 and -1, 1 and -1, and as you can see, they will give the result that you might expect from an OR operation. Here's some more examples. As you can see with this last one, again, when you compare the equivalent values in positive and negative decimal, you end up with all the bits set to 1. So let's move on to the NOT operator. NOT takes a single operand and flips all the bits. So we're showing the decimal values here because that's what the helper function does, but it's really kind of irrelevant. All that matters really is that you can see all the bits are flipped. If you have a negative value to start with, you will end up with a positive one because bit 64 will get flipped. Exclusive OR is a bit different. It will give you a 1 if the bit values are opposite. This second example is a bit better because you can see more easily what is going on. All of the bits higher than bit 4 are opposite, so we've got 0s and 1s, so they're all set to 1. The few bits that actually make up the values 10 and -5 over here, you can see what's going on. If they're both the same, as in here, here and here, so that's bit 1, 2 and 3, they will end up as 0s because they're the same. So this is the exact opposite of using OR. Here's a few more examples. Well, it might not seem obvious from these examples, if you do happen to compare the same values, you will end up with all 0s. So that's OR, NOT and XOR. Let's move on to bitwise shift operations. There are 2 bitwise shift operations, shift left and shift right. The operators in GDScript are pairs of angle brackets pointing to the left or right respectively. As the name suggests, they move bits left and right. You must also specify how many places to move left or right. Until bits start falling off at each end, shifting by 1 bit left or right is equivalent to multiplying by 2 or dividing by 2 respectively. Up to Godot 4.0, bitwise shift operations were only allowed on positive integers, although this might have been fixed in one of the maintenance releases. In Godot 4.1 and later, we can definitely use bitwise shift with any integer. An example of why you might use shift operations is for a stack of flags, although you would need to have checks for overflow conditions. Bitwise shift makes more sense when you see it in action. Let's run the project and see what we get. Let's hit run. And again, we're just getting the results in the output section, so we don't need this. So if we scroll to the top with our first shift left example, you can see we shift 6 times in each of these demos. If we start with a low value such as 24, you can see that the bits are gradually shifting right and we're eventually losing bits off the end and we end up with 0. If we do negative numbers, you can see that the zeros drop off in this case because we're adding ones at the beginning. Let's have a look at some large numbers using shift left. As you can see, when we shift left, the 64th bit 63, keeps flipping between 0 and 1 depending on what's moving to the left. This means that the decimal values of the number flip between positive and negative numbers. I mentioned earlier that I have a helper function to display all of the bits in an integer. Godot will convert an integer to a string that shows the value in binary, but it only shows as many bits as are needed, and negative numbers are not shown in the way that they are actually stored as an integer. As you can see, we loop through 64 times, which gives us a value of n from 0 to 63. This sets a bit mask that is 2 to the power of n. Then we use Bitwise AND to see if the bit is set or not. And lastly, we come to the explanation I promised as to why negative integers look back to front when we look at how they are stored in binary form. This is because they are stored using an algorithm known as 2's complement. If I do not explain this well enough, please feel free to check out online explanations, such as the Wikipedia page for 2's complement. There are 3 steps to this algorithm. We'll use an 8-bit example because that will make it easier to see what's going on. The algorithm is exactly the same for any size integer using 2's complement. First, begin with the equivalent positive number. Next, flip all of the bits so that 1s become 0s and 0s become 1s. Finally, add 1 to the number, and if it overflows, discard the overflow digit. The reason for using 2's complement is that it simplifies certain operations in the processor, but particularly subtraction. If you have watched part 2 of this series, you will have also seen how this affects overflow conditions, so that overflow switches between the maximum positive and negative numbers in a useful way that can be easily detected. 2's complement also dodges some problems with other binary schemes that allow strangenesses such as -0. Historically, this is not a new algorithm. Complement algorithms can be used in any number-based system. For example, before the advent of electronic computing, mechanical calculators used 9's complement and sometimes 10's complement. Hopefully you can also see now why the range is not quite symmetrical when using the 2's complement scheme. That is, the positive range is 1 less than the negative range. It is simply because the positive range starts at 0, whereas the negative range starts at -1. That's it for this series about integers. If you haven't seen them already, parts 1 and 2 of this series are available on my channel. I hope you find this information useful in your Godot journey. Please give this video a like if that's the case. And please subscribe to get future Symbalis videos in your subscription feed. Until next time, thanks for watching and stay safe.